3.2, differentiability. So in 3.1, we talked about how differentiation is pretty much the process of finding the derivative. In this section, we're going to focus more on the concept of differentiability itself. So if a function is differentiable at x equals c, then the function is continuous. So what I want you to do right now is pause the video and think about what it means for a function to be differentiable at a point. So this means we can find the slope of the tangent line to the graph of the function at that point, since the derivative of a function at a point is the slope of the tangent line to the graph at that point. This implies that the function must be continuous there. There is no tangent line at a discontinuity. So think about that. If a function has a discontinuity, if a function has some kind of break, can you draw the tangent line at that point of discontinuity? So graphically speaking, if you have a graph where there is a break on the graph, that means it's not continuous. But furthermore, can you draw the tangent line at that break? You can't. Okay, we'll go over more examples like that later on or in the next slides. The contrapositive, always true. If a function is not continuous at x equals c, then the function is not differentiable at x equals c. The converse, not always true. If a function is continuous at x equals c, then the function is differentiable at x equals c. So let's look at some examples. Here's an example of the contrapositive. Here we have a function that is not continuous, so there's obviously a break here on the graph. A discontinuity will cause one or both of the one-sided limits to be non-existent. So here in this gap, we can't draw the tangent line for this function. Okay, here at this break. Examples of the converse. So here we have two graphs. So f of x is equal to the absolute value of x, and f of x is equal to x to the 2/3. So in this first graph, at x equals 0, we have what's called a corner here. A corner where the one-sided derivatives differ. Okay, so you can't draw a tangent line. Okay, you can't draw one given tangent line at this corner. Okay, you got this, you got that. Okay, you can't just draw one tangent line. Okay, look at all of these tangent lines or so-called tangent lines that would exist at this point, at this corner. We don't say that there's an infinite amount of tangent lines. We just say that it's not differentiable there. The same concept goes here at what we call a cusp, where the slope approaches positive infinity from one side and negative infinity from the other side. Same concept. Okay? It's not differentiable there. Okay, and we can keep going on forever. So a vertical tangent line where the slopes approach either positive or negative infinity from both sides. For example, the function f of x is equal to the cube root of x. Oops. not differentiable there. Okay? So this leads us to the alternate form of the derivative. The derivative of f at x equals c is given by f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. To show this limit exists, we got to go back to this concept that we learned in the last chapter. Okay, this should all be familiar. Look familiar? The derivative from the left should equal the derivative from the left should equal the derivative from the right. So let's look at an example. So find the derivatives from the left and from the right at x equals 1 if they exist. Is the function differentiable at x equals 1? So here we have a piecewise function, x when x is less than or equal to 1, and x squared when x is greater than 1. Okay, so like the alternate form of the derivative states, we have to show that the derivative from the left is equal to the derivative from the right. So derivative from the left so that's the limit as x approaches c from the negative side of f of x minus f of c over x minus c. Well, in this case, c is 1. So I'm going to go ahead and put more specifically the limit as x approaches 1 from the negative side of f of x minus f of 1 over x minus 1. So remember, quick refresher, x is less than 1. That's what we should be thinking about when x is approaching 1 from the negative side. So we're talking about the first function x. So we get the limit as x approaches 1 of x minus, when we plug in 1 into x, we just get 1 over x minus 1. Then we can do this. That's 1 over 1. So the limit is just 1. Okay, so let's check it with the derivative from the right. Okay, so again, we have the limit as x approaches c from the positive side this time of f of x minus f of c over x minus c. Okay, so let's apply it with the problem that we have. The limit as x approaches 1 from the positive side of f of x minus f of 1 all over x minus 1. Once again, x is greater than 1 is what you should be thinking about when x approaches 1 from the positive side. So that's the function x squared. Okay? So we get the limit as x approaches 1 of x squared. And when you plug in 1 into x squared, that's just 1 squared, which is just, so it's 1 squared. So we just get, it's the same as just putting 1. So x squared minus 1 over x minus 1. Okay? Direct substitution right now will produce 0 over 0. Okay? And the algebra that we can do here is pretty much factoring the numerator. So x plus 1, x minus 1, over x minus 1. This happens. So we get the limit as x approaches 1 of x plus 1, which is 2. Okay, so from the left, our derivative was 1. From the right, the derivative is 2. So they're not equal. The derivative does not exist. Go ahead and write this down. Since the derivative from the left does not equal the derivative from the right, at x equals 1, f of x is not differentiable. At x equals 1. Okay? And if we graph it, so go ahead and draw the graph. If we graph it, we can see that at x equals 1, we have a cusp. Okay? Kind of like a point. It's like a mix of a corner and a cusp. Okay? So it kind of does. So we have the line. We have this line with a positive slope of 1. Okay? And then it breaks off to the parabola doing something like, so we go from a line to a curve. So this is a point that we call a cusp. Okay? That's kind of what's going on here. It's just kind of hard to see because the drawing is not the best graph with this with the technology that I have. But if you graph it in your graphing calculators, you might get a better picture of it. Okay? And that is it for this video.